Regression diagnostics mostly concern statistical significance of the regression line, the slope, and the intercept. There are more than a dozen statistics that address every aspect of the regression. Excel will crank out all of them. Only a few are important in general use, and only one is essential to anyone using simple linear regression. The absolute must-know statistics in simple linear regression is R squared. The official name is the coefficient of determination. Nobody talks like that, even statisticians, so it's just called R square. R square is the square of R, the linear correlation coefficient. The official name for R is the Pearson product moment correlation coefficient. That's why it's called R. If you already know about R, skip ahead a little. Otherwise, here it is. R measures the strength of the linear relation between two variables. R has nothing to say about nonlinear relations. R is between -1 and +1. R equals -1 indicates a perfect negative linear relation, and R equals +1 indicates a perfect positive linear relation. R near 0 means no relation. Correlation has no dependent and independent variables. X and Y or Y and X are the same. R square has a different interpretation. R square is always positive since it's a square. R squared, expressed as a percent, is the amount of the variation in the dependent variable Y associated with the independent variable X. Imagine a bucket containing the variance of Y values. Everything we don't know about Y is in the bucket. We have a sponge called regression, full of X values. We put the sponge in the bucket. The sponge absorbs all it can of the variation in Y. Pull the sponge out. That amount of variation of Y in the sponge is the percent R square. An R square of 0.8 means 80% of the variation in Y comes out with the sponge. 100% minus 80% is the amount of variation in Y remaining in the bucket, called the residual. An R square near 0 means X has little association with Y. The regression predictions will not be reliable. R square near 1 means the regression predictions are very reliable. There are two caveats with R square. First, R square is frequently described as the amount of variation in Y that is explained by X. X doesn't explain Y. Statistics cannot prove cause and effect. A better term is associated, or even happens to go along with. Explanation is just an easier way to describe R square. For example, predicting the number of people per year who died by becoming tangled in their bed sheets from the per capita yearly cheese consumption has an R square of 90%. Clearly, cheese consumption can't explain malicious sheets. Second, a high or low value of R square depends on the field of study. If you are predicting fish weight from fish length, you would think there is a problem if R square is less than 90%. If you are dealing with social predictions, such as political party affiliation and income, you would be amazed if R square was as high as 30%. There is a statistical test for the significance of R-square. Basically, it's useless. R-square depends more on the circumstance than on any test of significance. Other diagnostics are for the fit of the regression line and confidence intervals for the slope and intercept. These aren't as important as R-square, but are frequently requested. These diagnostics require using the regression function in the Excel analysis tool pack. The analysis tool pack is already in Excel. You just have to make it visible. Instructions for making it visible are elsewhere. When the analysis tool pack is activated, Data Analysis will appear in the upper right-hand corner of the Data menu tab. Click on Data Analysis to go to the Analysis menu. Scroll down and select the regression function. The regression function requires only a Y range, an X range, and an output range. Everything else is optional. This is the completed regression function. Shown are the range of the dependent variable Y, the range of the independent variable X, and where to put the results. The output has lots of pieces. Don't be intimidated. Some are repeats and others aren't needed. Also, the number of decimal places exceeds any possible use. With fewer decimals, it looks better. I will cut off some of the decimals when we get to the specifics. The upper table is labeled Summary Output. The first item is multiple R. Multiple R is simply the linear correlation coefficient between X and Y for simple linear regression, except that it is never negative, even when the relation is negative. The multiple part comes from this label being used with two or more independent variables. You can't calculate a correlation coefficient between three variables, one Y and two or more X's. So this is really the square root of R squared, not a correlation coefficient. Multiple R is a name that simply covers all the bases for regression in general. R squared, 0.671 or 67.1%, is the amount of variation in Y associated with X. The next entry, adjusted R squared, is the regular R squared adjusted for the number of independent variables. Adding independent variables will always raise the R squared, even if the added variables have nothing to do with Y. In fact, you can make the R squared equal to 1 by having as many independent variables as Y observations, regardless of any relation. This isn't useful in simple linear regression. The standard error of regression is very important in calculations of reliability for slope and intercept. It also ties back to why is it called least squares. But you don't need it unless you want to see the calculations. Observations is the sample size. It's included because someone thought it should be. The ANOVA section summarizes the distribution of variance for the general linear model of which simple linear regression is a part. That's a whole lot of statistics talk that means, is the regression useful? The SS column is the sum of squares attributable to the regression, the residual, and the total. Going back to the bucket, the total sum of squares is everything in the bucket before we put in the sponge. The regression sum of squares is how much came out in the sponge. The residual sum of squares represents how much remains in the bucket. This makes more sense as percentages. The total is 100%. The regression is 67.1%, and the residual is 32.9%. Notice that the regression percent is R square. This is where it comes from. Beyond the percentages of sums of squares, only the F statistic is important. F measures the significance of the regression. Think of it as another version of R square. Roughly speaking, if F is greater than 4, the regression is significant. This F value is 57. It is very significant. The actual significance is to the right of F. Use this to test significance of regression if you want to be proper. The other two items worth mentioning are the residual sum of squares and the residual mean square. The residual sum of squares appears again in why is it called least squares. The standard error in the summary output box is the square root of the residual mean square. The table below ANOVA shows the intercept and slope in the coefficients column. The intercept is labeled intercept, so it's easy to find. The slope, however, is indicated by the name of the independent variable. You can put a name when the regression is set up, but the default isn't a problem in simple linear regression. There's only one independent variable. All other entries in the slope and intercept rows concern the statistical significance of the intercept and slope. If you're familiar with t-values and p-values, you can use them for tests of significance. But the easiest way is the confidence interval columns. Confidence intervals can be thought of what could have been if another set of data was gathered for the same situation. The intercept could have been as low as minus 6.241 or as high as 19.779. This range includes 0. The line could have gone through the origin. The what could have been for the slope ranges from 0.609 to 1.063. This does not include 0, so we can say that the line could not be flat. These are not tests for a specific value of the intercept and slope, only that neither is 0. If you suspect the slope or intercept should be a specific value, you would need to do a specific test for that value. Testing for a 0 slope is not useful. If I thought the slope could be 0, I wouldn't have done the regression at all. The test for the intercept is only slightly more useful, but we need to have a reason to believe the intercept could be 0. If the phenomenon being studied can really have a 0 intercept, such as distance traveled by time, then we have a reason to test for a 0 intercept. All in all, you need to be familiar with these test statistics because someone might ask about them. Otherwise, take the intercept and slope and leave the rest. Incidentally, the 95% confidence interval columns are duplicated. The first lower and upper is the default 95% interval. You choose the confidence level for the second lower and upper in the regression function. Otherwise, it's 95% as well. Other diagnostics tools are optional in the regression function. Below the input range fields are labels, constant is 0, and confidence level. Checking labels makes the first entry in the input column range the name of the variable. If you see a number as a label in the output, you have checked the box by mistake. Checking constant is 0 forces a 0 intercept on the regression. Don't check this box. Forcing a 0 intercept messes up many of the values of the diagnostics, including the R-square. Checking the confidence level box and selecting a confidence level puts that information in the second confidence interval column in the output for intercept and slope. Use it if you want something other than a 95% interval. The lower third of the regression function concerns residuals and several plots. Residuals are the prediction errors from the regression line. These can easily be calculated in the spreadsheet, but they don't hurt anything if requested. 3 plots are optional in this portion: residual plots, line fit plots, and normal probability plots. The residual plot is the only useful plot. A good regression will have a uniform spread of residuals. That means there is no pattern to the prediction errors. A flare or unevenness in the residual means the data has a pattern that should be removed by transformation. This is a very small scale plot. You can make a better one with the information provided by the list of residuals. The variable line plot is simply the regression line and data. That's easily done by adding a trend line to a scatter plot. The small scale of this plot makes it why bother. The normal probability plot tests the assumption that the dependent variables are normally distributed. If the assumption is correct, the plot should show a straight line. Basically, the line is never straight, and how straight is straight enough anyway? This is on a very small scale. There are better normality tests available. Use one of these if you want to test normality. The test for normality brings up another problem. Most regression assumptions are honored more in the breach than in observance. After all, are you going to collect another data set if an assumption is violated? You probably get what you already have. A call to the robust nature of regression usually settles any argument about assumptions. Always remember robust. It's the abracadabra of statistics.